We want to show that 3 divided by 2 times 3 divided by 3 times 3 divided by 4 times 3 divided by 5 times the rest of the terms, 3 divided by n minus 1 is less than equals to 3 halves. Or basically, we want to show that 3 divided by 3 times 3 divided by 4 times 3 divided by 5 times 3 divided by n minus 1 is less than equals to 1. We can use the method of induction to prove this. In the method of induction, if you have Pn, which is just a statement in n, we start by an inductive step. Inductive step is using the smallest value in the domain and show that it is true for that smallest value. For example, P of 1 or P of 2 or any number that is the smallest value in the domain, P of the smallest value is true. Okay, so what is the smallest value here? When you're writing P of n, n is equal to 3 gives you the smallest value. So here you have P of 3. P of 3 is basically saying that, hey, if I multiply 3 divided by 3 minus 1, it must be less than equals to 3 divided by 2, but it is true all the time. Left-hand side is 3 divided by 3 minus 1, and on the right-hand side, you have 3 divided by 2, which is true all the time. Now, inductive hypothesis. The inductive hypothesis says if pk is true, we should be able to prove it for pk plus 1. So what are we going to do? We're going to assume that we are in this step, hypothesis, inductive hypothesis. So what is pk? pk says the multiplication of 3 divided by 2 by 3 divided by 3 by 3 divided by 4 dot 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 by 3 divided by k minus 1 is less than equals to 3 divided by 2. Our goal is to show that pk plus 1 is also true. So we want to show that pk plus 1, so this is assume it is true. We want to show that pk plus 1 is also true with a question mark on top of it. So what is pk plus 1? pk plus 1 can be written as 3 divided by 2 times 3 divided by 3 times 3 divided by 4 times dot 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 times 3 divided by k minus 1 times 3 divided by k plus 1 minus 1. Is this guy is also less than equals to 3 over 2? Well, let's see. So the very first multiplication here between 3 divided by 2, 3 divided by 3, 3 divided by 4, 3 divided by k minus 1 indeed is less than equals to 3 over 2. So for sure you can say that, hey, since pk is true, 3 over 2 times 3 over 3 times 3 over 4 dot 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 3 over k minus 1 multiplied by 3 divided by k plus 1 minus 1, or k is indeed less than equals to 3 divided by 2 times 3 divided by k. Again, this multiplication indeed is true because it is pk. Now, the only thing you need to do is to analyze 3 times 3 divided by 2 times k. We're going to show that this guy is also less than equals to 3 divided by 2. But from pure algebra, since 3 over 2 times 3 over k is equal to 9 over 2k, am I right? But when you're thinking about 3 over k, what do we see here? Note that the smallest value in our domain, when we went back here, the smallest value in our domain was k, right? K minus 1, k is more than or equals to 3, right? So 3 divided by k is less than equals to 1. So if I multiply both sides by 3 over 2, 3 over k times 3 over 2 is also less than 3 over 2. So I just proved this part. So by the method of induction, we showed that 3 divided by 2 times 3 divided by 3 times 3 divided by 4 times 3 divided by 5 times 3 divided by k minus 1 is always less than or equals to 3 divided by 2. Now we're going to use this and find the limit. Now find the limit of the sequence an, which is equal to 3 to power n, divided by n factorial. In order to find the limit of 3 to the n divided by n factorial as n goes to infinity, if you use direct substitution, you get infinity over infinity. You cannot apply L'Hopital's rule because you have a lot of multiplication on the denominator. So forget about L'Hopital's rule. What are you going to do instead? You're going to find the lower bound and upper bound for this sequence and use squeeze theorem. So our goal is to use squeeze theorem. So let us find a lower bound and upper bound for this sequence. An upper bound for sequence 3 over n, 3 to the n divided by n factorial. So let us break this guy down into smaller pieces. 3 to the n divided by n factorial is 3 times 3 times 3 times 3, and continue this process, times 3 divided by n factorial is 1 times 2 times 3 times 4 dot 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 times n minus 1 times n. Very good. If you rewrite this, you have 3 over 1 times 3 over 2 times 3 over 3 times dot 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 times 3 over n minus 1 times 3 over n. From induction here, we know that, take a look, we know that 3 divided by 2 times 3 divided by 3 times 3 divided by n minus 1 is less than equals to 3 over 2. We just showed it using induction. We know that this is less than equals to 3 divided by 2. But what is this quantity? This quantity is the middle quantity here. So if I multiply both sides by 3 over 1 and 3 over n, this is what I get. Three over 1, 3 over 1, and then multiplied by 3 over n. Very good. So the sequence on the left-hand side is nothing but 3 to the n over n factorial. And on the right-hand side, it is less than or equals to 27 over 2n, which is a simpler sequence. It is simpler in the sense that you can easily find the limit of this sequence. But what is the limit of this sequence? The limit of 27 divided by 2n as n goes to infinity is 27 divided by infinity or 0. Also note that this guy is more than 0. So the limit on the left is 0, the limit on the right is 0. If you have applied the squeeze theorem, the limit of 3 to the n divided by n factorial as n goes to infinity must be equal to 0. So the sequence is convergent. You can also use this sequence and find the sequence of something like this. If I ask you to find the limit of the sequence negative 3 to power n divided by n factorial as n goes to infinity, you can say that we want to apply the theorem below that says that if the limit of absolute value of an as n goes to infinity is equal to 0, then we can conclude that the limit of an as n goes to infinity is equal to 0. But since the absolute value of negative 3 to power n divided by n factorial is equal to 3 to the n, let me write down everything for you, is the absolute value of negative 1 to power n times 3 to power n divided by n factorial, which is equal to absolute value negative 1 to power n times 3 to the n divided by n factorial. And this is indeed equals to 3 to the n divided by n factorial. And we just showed that. This sequence is convergent to 0 so as the sequence negative 3 to power n divided by n factorial. This guy is also convergent to 0 by the theorem. Converges to 0 using the theorem above. So let us recap what we did. We are applying the method of induction to show that this fraction 3 divided by 2 times 3 divided by 3 times 3 over 4 times 3 over 5 times 3 over n minus 1 is less than equals to 3 over 2. So we can find the upper bound for this multiplication. By the method of induction, we say that if we have a general term like Pn, it can be any term in n, any statement in n. To prove using induction, we have inductive step. First, we show that the statement is true for the smallest value in the domain. Well, in this case, we start by taking n to be equals to, for example, 3 itself. The smallest denominator is 2. So don't go lower than 3. So P of 3 is 3 divided by 2, which is less than equals to 3 over 2, which is true. Now, inductive hypothesis says if pk is true, you can show that pk plus 1 is true. So if pk is true, it means that this multiplication or this inequality is true. To show that pk plus 1 is true, you just substitute k plus 1 for k on the denominator, but it doesn't eliminate the term that you have below it. But at the same time, 3 divided by 2 times 3 divided by 3 times 3 divided by k minus 1 is basically using inductive hypothesis less than equals to 3 over 2. And we multiply it by 3 over k. Since k is more than equals to 3, k, if you divide everything by k, 3 over k is less than equals to 1. And if you multiply both sides by 3 over 2, 3 over 2 is more than equals to 3 over k times 3 over 2. So you just showed that this quantity, this multiplication, or indeed this larger multiplication is less than equals to 3 over 2. So by the method of induction, we showed that this multiplication indeed has an upper bound, which is 3 over 2. Now we find the limit of a sequence, which is 3 to the n divided by n factorial. If you use direct substitution, you get infinity over infinity. We're not going to apply L'Hopital's rule. Instead, we're going to use the squeeze theorem. First of all, 3 to the n over n factorial can be broken down into the multiplication of 3 by 3 by 3 by 3 over 1 times 2 times 3 times 4 to n. But we just showed that the middle term here, this multiplication is less than equals to 3 over n. Since this guy is less than equals to 3 over 2, so you can show that if you multiply both sides by 3 over n and 3, it is true as well. But why we did that? Because we wanted to find the upper bound for this multiplication. Why upper bound is important? Because if we find the limit of the upper bound, and it is also equal to 0, you can apply squeeze theorem and say that, hey, the limit on the left and the limit on the right are both equal to 0. Basically, the limit of the middle function or middle sequence is indeed equal to 0. So the sequence is convergent. You can also use these information and find the limit of another sequence, which is negative 3 to power n divided by n factorial as n goes to infinity. You want to apply the theorem that says, hey, if the limit of absolute value of an is equal to 0, you can conclude that the limit of an is also 0 as well. So if you take the absolute value of the sequence, the absolute value is 3 to the n divided by n factorial. You already showed that the limit of this sequence is equal to 0. So by applying the theorem, you can conclude that the limit of an is equal to 0 as well.